Hello friends, we start a class on sequence of function. This is our 9th class, okay? This is our 9th class. In previous classes, we discussed a consequence on uniform convergence and some examples. In this class, we discuss another theorem on uniform convergence, okay? And examples, okay? And some examples. Okay, so let us start. Theorem. If let I be a closed and bounded interval and this is a sequence of function on AB, okay, or I, okay. I be a closed and bounded interval and this sequence of function is a sequence, this is a sequence of function on I, okay. Let for each n belongs to n, fn from I to R be remain integrable and the sequence of function is uniformly convergent to f on I, okay. This is a sequence of function and each fn is remain integrable and the sequence of function is uniformly convergent to f. Then the limit function f is also remain integrable, okay. Then the limit function is also remain integrable and the sequence integration a to b fn, this sequence converges to this sequence converges to this. In other words, limit of this sequence, limit n tends to infinity, this sequence integration a to b fn x dx, this is equal to this integration a to b, f means limit n tends to infinity fn x, okay, dx. Clear? So this theorem says that if fn is a sequence of function on a closed and bounded interval and each fn is remain integrable on I and the sequence of function is uniformly converges to f, okay, not pointless convergent, uniformly converges to f on I, then the limit function is also remain integrable. Clear? And the limit and the integration can be interchanged, okay. The limit and the integration can be interchanged. Clear? So now we prove this. Okay. Proof. Since this sequence of function uniformly converges to f, so by definition for each epsilon greater than 0 there exists natural number k belongs to n such that mod of fn x minus fx is less than epsilon. We take epsilon by 4 into b minus a, okay, for all n greater than equal to k, okay. We take epsilon or epsilon by 2 or epsilon by 3 in my choice, okay. So we take epsilon by 4 into b minus a. Clear? Since b not equal to a, because this is an closed interval, so a not equal to b, so b minus a is not equal to 0, okay. Clear? So by the definition of uniform convergence, for each epsilon greater than 0 there exists k belongs to n such that this is holds for all n greater than equal to k. So for n equal to k, this inequality also holds. So for n equal to k, fkx, therefore fkx minus fx is less than epsilon by 4 into b minus a. Clear? So this is same as fx minus fkx is less than epsilon by 4 into b minus a. Okay. So to remove the mod, we get fkx minus epsilon by 4 into b minus a is less than fx is less than fkx plus epsilon by 4 into b minus a. Okay. Clear? Okay. If we remove the mod, we get this. This is take as 1. This is true, this is true, this is true for all x belongs to AB. Okay. This is true for all x belongs to AB. This is true for all x belongs to AB. Clear? Therefore, this is true for all x belongs to. This is true for all x belongs to AB. Okay. Again, since for all n fn b remain integrable. Okay. For all n fn b remain integrable. So fk is remain integrable. So fk is remain integrable. So by the necessary and sufficient condition of integrability, we have this is remain integrable on AB. Okay, this is our domain. Our domain is AB. Okay, so this is remain integrable. So by the necessary and sufficient condition, for each epsilon greater than 0, there exists a partition. There is a partition P. We take P as equal to x0 less than xn less than x1 less than x2 less than less than xn equal to b. Okay, this is our partition. So there is a partition P of AB satisfying UPF, that is here our function is fk. Okay, UPF minus LPF. Okay, our function is fk. Fk is an integral, so UPFk minus LPFk. This is less than epsilon. We take this is less than epsilon by 2. Okay, and take as number 2. Okay, take it number 2. Clear? Now we take the supremum and infimum of fx and fkx. Okay, so we take capital M r equal to supremum of fx, x belongs to xr minus 1 comma xr. Okay, and a small m r equal to infimum of fx, x belongs to xr minus 1 comma xr. Okay, similarly a small m r dash equal to supremum of fkx, x belongs to xr minus 1 comma xr, and a small m r dash equal to infimum of fkx, x belongs to xr minus 1 comma xr. Clear? We take supremum and infimum of fx and fkx. Now from 1 we have fx is less than fkx plus epsilon by 4 into b minus a. Okay, clear? Okay, since from 1 fx is less than fkx plus 4 into fkx plus epsilon by 4 into b minus a. Okay, so if we take supremum in the both sides, we have, if we take supremum as x belongs to this, if we get supremum in both sides as x belongs to xr minus 1 comma xr, we have this is mr, because supremum of fx is mr, which is, and if you take supremum, then less than may be less than equal to, and less than equal to for fkx, supremum is mr dash plus epsilon by 4 into b minus a. Okay, Similarly from 1, fkx minus epsilon by 4 into b minus a is less than fx. Okay, since in 1 fkx minus epsilon by 4 into b minus a is less than fx. If we take infimum to the both side, for fkx infimum is mr dash. So mr dash minus epsilon by 4 into b minus a, this is less than equal to mr. Clear? Okay. Now we calculate UPF and LPF because we have to find we have to prove that f is Riemann integrable. Okay, so we prove UPF minus LPF is less than epsilon. Okay, so first we find UPF. Okay, UPF means summation r equal to 1 to n mr xr minus xr minus 1. Clear? Now capital MR is less than equal to this. So this is less than equal to summation r equal to 1 to n mr dash plus epsilon by 4 into b minus a. Clear? xr minus 1. Okay, so this equal to summation r equal to 1 to n mr dash xr minus 1 plus this is common part, so epsilon by 4 into b minus a summation r equal to 1 to n xr minus 1. Okay, clear? So this is UPF. Here mr is the supremum of fx and mr dash is the supremum of fkx. So this is our UPFK. Okay, UPFK plus epsilon by 4 into b minus a. If we calculate this, we write this in the rough summation xr minus 1. Okay, r equal to 1 to n. So this is x1 minus x0 plus x2 minus x1 plus x3 minus x2 plus xn minus 1 minus xn minus 2 plus xn minus xn minus 1. Okay, so since x1 is cancelled out, x2 is cancelled out, similarly x3 will be cancelled out, and so on. xn minus 2 cancel out, xn minus 1 cancel out, ultimately xn minus x0. Okay, that is b minus a, because p is a partition on AB. P is a partition on AB. So A equal to x0 and xn equal to b. So xn minus x0 equal to b minus a. So this sum is b minus a. Okay. Since b minus a not equal to 0, so this is cancelled out. So this implies UPF. Therefore UPF is less than equal to this. Therefore UPF is less than equal to UPFK plus epsilon by 4. Okay, clear? Similarly, if we calculate LPF, LPF equal to, what is this? R equal to 1 to n small mr xr minus xr minus 1. Okay, since a small mr is greater than equal to this, since a small mr is greater than equal to this, so here we get by similar calculation, okay, as UPF. By similar calculation as UPF, we get this is greater than equal to LPFK minus epsilon by 4, okay. By similar calculation as UPF, we get LPF is greater than equal to LPFK minus epsilon by 4, okay. So therefore minus LPF, the inequality is less than equal to, is it minus of LPFK minus epsilon by 4, okay. This implies minus LPF is less than equal to minus LPFK plus epsilon by 4, okay, clear. So UPF is less than equal to this, and minus LPF is less than equal to this. So if we add this, this take as 3 and this take as 4. If we add 3 and 4, UPF minus LPF is less than equal to UPFK minus LPFK, okay, plus epsilon by 2, okay. This is equal to epsilon by 2, okay, clear, equal to epsilon by 2. Now since from 2 this is less than epsilon by 2, UPFK minus LPFK is less than epsilon by 2, so UPFK minus LPFK less than epsilon by 2, this is less than epsilon by 2 plus epsilon by 2, that is epsilon. Therefore UPF minus LPF, this is less than epsilon, okay. Then by necessary and sufficient condition for integrability, f is Riemann integrable on AB, okay, f is Riemann integrable on AB. So this is proved, f is also Riemann integrable, okay. Now we have to prove the second part, this sequence converges to this, okay. Now the second part, okay. In second part we have to prove that this sequence converges to this, okay. This sequence converges to this, okay. We have to prove that. In second part we have to prove that this sequence converges to this, okay. That is we have to prove that mod of integration a to b fnx dx minus integration a to b fx dx, this is less than epsilon, okay. For a PSN epsilon, this mod is less than epsilon, okay. If we prove this, we say this sequence is converges to this, okay. So we have to prove this, okay. So let us start. Given that the sequence of function is uniformly converges to f, okay. So for each epsilon greater than 0 there exists natural number k belongs to n such that mod of fnx minus fx is less than epsilon by 2 into b minus a. We can take any epsilon, okay. So we can take we take epsilon by 2 into b minus a for all n greater than or equal to k. Clear? Now mod of integration a to b fn x dx minus integration a to b fx dx. Okay, this. Okay, we take this. Okay, we take this. Okay, we will prove this is less than epsilon. So this is equal to mod of integration a to b fn x minus fx dx. Okay, now in Riemann integration chapter, in the chapter Riemann integration, we have a result. If f is Riemann integrable, then mod of integration a to b f, this is less than or equal to integration a to b mod f. Okay, this is a result on Riemann integration. Okay, so use this result. Mod of this is less than or equal to integration a to b mod of fn x minus fx dx. Okay, clear? Now mod of this is less than epsilon by 2 into b minus a. So if we integrate both sides, this less than maybe less than equal to, so this is less than equal to integration a to b. We replace this by this epsilon by 2 into b minus a. This is less than epsilon by 2 into b minus a. So if we integrate both sides, maybe less than equal to, so this is less than equal to integration a to b epsilon by 2 into b minus a dx. Okay, so this is a constant term, so this is 2 into b minus a into integration a to b dx. Okay, so if we integrate this is equal to epsilon by 2 into b minus a, this is b minus a. So since b minus a not equal to 0, b minus a cancel out. This is equal to epsilon by 2, which is less than epsilon. So mod of this is less than epsilon, therefore mod of integration a to b fn x dx minus integration a to b fx dx is less than epsilon. Okay, this is less than epsilon for all n greater than or equal to k, because this is less than or equal to this for all n greater than or equal to k. Okay, this is less than this for all n greater than or equal to k. So for this is less than equal to this for all n greater than or equal to k. So this is less than epsilon for all n greater than or equal to k. Okay, this implies integration a to b fn x dx converges to integration a to b fx dx. Okay, clear? So this completes our proof. Okay, note. Okay, our note is if this is a sequence of function such that each fn is Riemann integrable. Okay, each fn is Riemann integrable on I. Each fn is Riemann integrable on I, but either on I and f be the limit function. Okay, if fn is a sequence of function such that each fn is Riemann integrable on I and f be the limit function, then if either either f is then number one f is not Riemann integrable implies the convergence is not uniform. Okay, if is not Riemann integrable, this implies the convergence is not uniform. And number two, f is Riemann integrable, but the sequence does not converge to integration to be f, then also the convergence is not uniform. Okay, so what is our note? If fn be a sequence of function such that each fn is Riemann integrable on I and f be the limit function, okay, then if f is not Riemann integrable, each fn is Riemann integrable, but if the limit function is not Riemann integrable, then we say the convergence is not uniform, because if fn uniformly converges to f and each fn is Riemann integrable, then the limit function must be Riemann integrable. If the limit function is not Riemann integrable, the convergence is not uniform. Also if the limit function is Riemann integrable, but this sequence does not converge to the limit this, then also we say the convergence is not uniform. Okay, so we give an example on this note. Okay, this is the example of mapa, page 571, old book, work example 9. Okay, so here f and x equal to nx into 1 minus x square whole to the power n. Okay, x belongs to 0, 1. Okay, x belongs to 0, 1. We prove that the sequence of function is not uniformly convergent. Okay, solution. We apply the above note. Okay, first we find the limit function. In class 6, we discuss example this. Okay, this is example of class 6. Fnx equal to nx into 1 minus x whole to the power n. Similar as this, nx into 1 minus x square, and here x. Okay, here x square and here x. Okay, similar type. So in class 6, this is the example of same type, and by similar process of this example. Okay, in our class 6 we discuss this example, and by the similar process of this example we can easily find the limit function of this is 0. Okay, So we avoid the limit function to find the limit function. Okay, we avoid the process to find the limit function. This is your HW. Okay, so just to write the sequence of function fn is pointwise convergent on 0 1, and the limit function is the limit function is fx equal to 0. Okay, and the limit function is fx equal to 0. Okay, for x belongs to close 0 1. Clear? So this the limit function you can find in. Okay, now we find the integration. Now we find this limit. Now we find this limit. Okay, now we find this limit. Okay, so the limit function since this is a polynomial. Okay, this is a polynomial in n, polynomial in x. This is a polynomial in x, and this is Riemann integrable because this is a continuous function, so this is Riemann integrable. Okay, and the limit function is also Riemann integrable. Now we check the limit, that is first we find limit n tends to infinity integration a to b fn x dx. Okay, so this equal to limit n tends to infinity, our AB is 0 1. Okay, 0 to 1, our AB is 0 to 1. So limit n tends to infinity 0 to 1 fn x dx equal limit n tends to infinity integration 0 to 1, our fn x is nx into 1 minus x square whole to the power n dx. Okay, clear? So roughly we find the integration. Okay, integration 0 to 1 nx 1 minus x square whole to the power n dx. Okay, if we take x square equal to z. Okay, so 2x dx equal to dz. So in 0 to 1 1 minus z to the power, if we take 1 minus x square equal to z, if we take 1 minus x square equal to z minus 2x dx equal to dz, then for x equal to 0 z equal to 1, for x equal to 0 z equal to 1, and for x equal to 1 z equal to 0. Okay, and it will be changed in z to the power n into dz by 2. Okay, there are a negative. Okay, there are a minus. Okay, clear? So this is equal to n into n, this is equal to n by 2. For this minus, the limit will be changed z to the power n dz. Okay, so this is equal to n by 2 into z to the power n plus 1 by n plus 1. Okay, 0 to 1, so this is n by 2 into n plus 1. Okay, so the integration is limit n tends to infinity n by 2 into n plus 1. Okay, so we find this limit in previous classes. Okay, this is 1 by 2 into 1 plus 1 by n. Okay, as n tends to infinity, this limit will be half. Okay, clear? So this limit is half, but integration 0 to 1 limit n tends to infinity fn x. Okay, dx. This is 0 to 1. This is our fx. Okay, the limit function limit n tends to infinity fn x. Okay, this is fx, our limit function, and fx is 0, so the integration is 0. So therefore limit integration a to b fn x dx is not equal to integration a to b limit fn x dx. Okay, these two limits does not equal, that is this sequence does not converge to this. Okay, this sequence does not converge to this. So this, by the above note, this implies the convergence is not uniform. Okay, the convergence is not uniform. Clear? So this note will help us to find or to prove a sequence of function is not uniformly convergent. Okay, this note will help us to prove the sequence of function is not uniformly convergent. Clear? Okay, that's it.